Hi there, everybody. Welcome to another Chem Complete lecture. And in today's lecture, this is just going to be a brief problem-solving session. And this is a follow-up video to a video I posted recently on how to determine equilibrium concentrations using ice calculations. And more specifically, I was looking at how you can use the square root method where it may be appropriate to do so. So we're going to do an additional practice problem here using the square root method. If none of this sounds familiar or you are looking for an initial rundown of how to perform these calculations, I encourage you to look at the first video that I did on this, and that lecture will give a lot more detail leading up to or leading into this. So I will also leave a link to that down in the section below in the description box in case you are looking for it. So with that said, let's go ahead and get started with determining the equilibrium concentrations using the square root method here. Okay, so a brief reminder, when we deal with ice calculations, the ICE acronym stands for initial concentrations, which will be given in the problem, the change in concentration, which we can usually write in terms of X, and then the equilibrium concentration, which will be the change from the initial, and that's what we are usually targeting in these problems. So here's the problem that I have for us to work on today. A reaction mixture initially contains both hydrogen gas and iodine at 0.750 molarity. And it's asking you to find the molarity or the concentration of H2, I2, and HI at equilibrium if the equilibrium constant is equal to 54.3. So if you remember, you're going to take your balanced equation and then you're going to set up an ice chart or an ice table where we can start labeling some of this. So the problem states that we start off with 0.750, and that's for both of these. So this one would also be 0.750. And remember, like we discussed last time, unless the problem states that you're already on the way to equilibrium and you have some amount of product, we're always going to assume that the product is 0 at the initial starting point. Okay, so the change here, we don't know how much is going to be lost, so we're just going to label it and say that we will lose some amount X, which we'll represent with a negative X, okay, and we will lose some amount X for the iodine as well. And over here we will gain some amount that we will call 2X. Now the 2 is coming from the balanced equation here, okay? So if you take a look, it's 2HI up here, and so therefore it's plus 2X when we deal with the change. So the equilibrium is going to be the initial amount that we had, and then we're going to take from that whatever the change is when we are headed towards that change in equilibrium. So 0.750 minus X for each of these, and that's going to come out to be a square term, and then this would just be 2X, because 0 plus 2X is going to return 2X to us. So we will come back to this line and these X values to solve the final problem, right? So now I want to set up the equilibrium expression and set it equal to KEQ. So the problem tells me that KEQ is equal to 54.3, so I can write that here. And that's going to equal, so it's products over reactants. The HI is represented as 2X at equilibrium, and that 2X term is going to be squared because there's a 2, and we always raise our exponents to whatever the value of the coefficient is. Okay, and that's going to be over. Now I have the same term down here for the reactants. It's 0.750 minus X, and I have it 2 times. So I can write down here 0.750 minus X, and because I'm multiplying it by itself, I can square that term. So this sets us up once again to use the square root method. I can take the square root of this side to cancel both of those squared terms. All I have to do is also take the square root of 54.3. So at this point, if you don't have a calculator, I would certainly encourage you to get a calculator out so you can practice this pause the video and see if you can solve it, or at least follow along at the bare minimum. Okay, so once we do this, what we are going to get is we can simplify it, and we can say, all right, the square root of 54.3 is going to be equal to 2x, and then that initial term that we had, but the square will be gone. Okay, so now here is a more simplified version of this. And in order to start simplifying it further, or to start solving for x, we're going to multiply each side by that denominator expression. So we'll get rid of it over here by multiplying this side and eliminating that. And then we are going to distribute the square root of 54.3. So if we take the square root of 54.3, we would get 7.37. And that's going to be times, because we have to also, right, multiply this side by the 0.750 minus x. Okay, and we have 0.750 minus x here equals 2x. And so now I want to distribute or multiply the value. So I'm going to multiply 7.37 times the 0.750, and then I'll also multiply 7.37 times negative x, and I will get a portionality that I can then start consolidating and getting the x over to one side. So 7.37 times the 0.750, if you put that into your calculator, you should get 5.53 minus, and it's just going to be 7.37x, and that's equal to 2x. Right, so now it's very easy for me to get x on one side. All I need to do is add 7.37x over here. That'll take care of that term and get rid of it. So I would also want to do the same thing over here. I'm going to add 7.37x. Right, so 2x plus 7.37x is going to be 9.37x, and that would be equal to the 5.53 that's left. So 5.53 is going to equal 9.37x. And now I can easily solve for x. All I need to do is divide. So I'll divide by 9.37. That'll just return x to me. And then I divide this side by 9.37. And so if you do that, you should find that x, in this case, is going to equal 0.590. Okay, so that's our x term. We are now going to solve in terms of the equilibrium. So let's look back up here just for a second. And I can see that it was 0.750 minus x for each of these terms. So I'll need to plug that 0.590 in place of the x and find the difference. And then to find the concentration of the HI, I'm going to need to take 2 times the 0.590. So let's go ahead and finish this problem up here. Okay, so for the H2 and the I2, we can write them both here because they have the same equilibrium concentration expression in terms of x, right? And they would equal 0.750 minus 0.590. And so some quick arithmetic on that would give us 0.160. So 0.160 molarity would be the answer for the H2 and the I2. And now the HI was represented as 2x. So what I'll do to solve for the HI is I'll take 2 times the 0.590, and that will return a value to me of 1.18 molarity. So there you go. Those are the answers. The H2 and the I2 concentration at equilibrium would be 0.160 molarity, and then the HI at equilibrium would be 1.18 molarity. Those are the final answers that address the problem. So hopefully this additional practice was useful. I'll probably post at least one more of them, and then we'll move on to quadratic equations and looking at how to solve these when the square root method does not apply. So thank you as always for choosing ChemComplete for your learning resources. You can head on over to chemcomplete.com. That's a great way to show us support. We have lots of free resources over there, and we also have very affordable guides for purchase that will help walk you through difficult content in general chemistry and organic chemistry. If you leave comments, I'll get back to you as soon as possible and try to engage with you. And other than that, remember to subscribe to stay up to date with your studies as you are going through chemistry class. And I will see everybody in the next lecture. Thanks for learning with me today.